Hi everyone, I want to share with you an introductory problem to our study of parametric equations. Hopefully this real life example will give you a better understanding of what parametric equations are and why we get a lot of use out of them. So in this problem, we have a wildlife preserve that extends 80 miles north and 120 miles east of a ranger station. A ranger leaves from a point 100 miles due east of the station and travels 0.6 miles north and 0.5 miles west every minute. A mountain lion leaves the western edge of the preserve 51 miles due north of the station. At the same time, the ranger starts making his way westward. Each minute, the lion travels 0.1 miles north and 0.3 miles east. If the ranger is out on patrol for an hour, will the ranger become the hungry mountain lion's lunch? So what we're going to do is start to maybe try to put together some equations and graph this so we can visualize it. And the last thing we'll do is take a look at how you could do this on your graphing calculator to have it graph it for you. So if you recall, you were told that the ranger is starting from a point 100 miles due east of the station. So suppose the station is at the origin of our coordinate graph. That means the ranger would be starting over here, and he's making his way up north and west, almost like a staircase. You're told the mountain lion is at a position 51 miles north of the station. So that would be about right here. And he's making his way north and east. And we're trying to basically see if the ranger's path and the mountain lion's path are going to cross. So what we're going to do is put together parametric equations. I like to think of parametric equations it almost looks like a system of equations in that they go in pairs. You're going to have an x equation and you're going to have a y equation, and each of those are in terms of a third variable that we call a parameter. In this case, we're going to use the parameter t for time. The x equation we're going to have is going to represent either the mountain lion or the ranger's horizontal motion going east-west. And the y equation is going to represent the mountain lion or the ranger's motion vertically, north-south. So let's start piecing those together. So let's start with the ranger's equations. Remember that he started at a position 100 miles due east of the station, and he's traveling 0.6 miles north and 0.5 miles west every minute. So if you think of that point on the coordinate axis that I put over on the right at 100, think of it as the ordered pair 100, 0. So in order to get the equation that's going to represent his path heading westward, he started at 100 and he's traveling west 0.5 miles every minute. So that would be the equation x equals 100 minus 0.5t. Now it's minus because heading west. Now in terms of his vertical motion, this is where you want to think of that ordered pair as 100, 0. His vertical position is at 0, sitting right on the x-axis. And you're told that he's moving 0.6 miles north every minute. So that's going to be the equation y equals 0 plus 0.6t. So that's the set of parametric equations to represent the ranger. So now we're going to do the same thing for the mountain lion. Now remember, the mountain lion started out at position 51 miles north of the station, and you're told the mountain lion is traveling 0.1 miles north and 0.3 miles east every minute. So in terms of the equation that represents his horizontal motion, remember that point, if you think of it in terms of the y-axis, that was up at 0, 51. That's the mountain lion's starting point. So in terms of the x equation, that's going to represent the mountain lion's horizontal motion, we would have 0 plus 0.3 t. Because remember, you were told the mountain lion was moving at a rate of 0.3 miles east every minute. In terms of the y equation, that's going to represent the mountain lion's vertical motion. Now remember, he started up at 51 miles north of the station, and you're told that the mountain lion's moving 0.1 miles north every minute. So that would be 51 plus 0.1 t. So let's go back to the graph and try to sketch this out just to get an idea. And then we'll take a look at it on the graphing calculator. And I think we'll then be able to answer our question. Let's do the ranger first. So you're told the ranger is moving north at a rate of 0.6 miles every minute and then also westward. So it's almost, and this is not going to be perfect. He's basically going up and over and then up, over, up, and over. Like I said, it's almost like a staircase. That's what he's doing. The mountain lion is going north 0.1 mile every minute and then east 0.3 miles every minute. So he's going up and then this way, up and then east, up and east, like that. So if you imagine extending each of those, they are eventually going to cross each other. It's just a matter of when, because remember, the ranger was only out on patrol for an hour. So we want to know if he gets eaten in that hour that he's out on patrol. So let's turn to the graphing calculator and we'll be able to explore this a little bit easier and a little bit more accurately. So to put your calculator into parametric mode, if you hit your mode button and you want to go down to the 5th line, you're always on function. That's all you've really ever known. You want to go over to the second one that says parametric. So you just go down, arrow down, then over on top of parametric, and then hit enter right on parametric. And when you hit y equals, you'll notice now you don't have y equals anymore. You have x1t, y1t. So you see how both of these, they're blue? X1t and y1t go together. So that they're the ones that I made the ranger. And then the red one, the x2t and the y2t, those two go together. That's who I made the mountain lion. And I just typed in those equations. You'll notice that now when you hit the X button, you'll get a T since you're in parametric mode. The other thing we'll have to do is set up our window. So you'll notice now your window looks a little bit different because now you have this third variable T, that parameter there. And otherwise, the X and the Y, that pretty much looks the same as you're used to it, but now you have the added part that you have to set up your T values. Now remember, the ranger was out on patrol for an hour, for 60 minutes, and since T is representing time, let's do 0 to 60. That will give us 1 hour. We can just do 1 for the step. That's like the increments you want to go on. And then for our X's, let's do 0 to 120. I'll just keep the scale Y, or 1. The Y min, we can do 0, and we can go up to maybe 80 or so for that, for the X max, or Y max. So now when you hit graph, you'll notice that, now remember, blue was the ranger and red was the mountain lion. So if you take a look at how it graphs, it does them both simultaneously. But this, what you see right now, is really where they were after 1 hour. In short, the ranger does not become lunch because they're really not that close together after 1 hour. Now, you could always extend this and ask the question, of course, at what point would their paths cross? So if we went back to our window, and let's try, instead of doing 1 hour, what if we did, I don't know, maybe 2 hours, like 120? Oh, still don't cross, but notice how they're a lot closer now. Pretty close. I would think the mountain lion could smell the ranger at this point, in which case he might start walking faster, but then that changes your equations and it's a whole other problem. But you can see at 2 hours, they're pretty close. If you were to keep playing with this, there is a way you can actually find when they do intersect, and it's actually at 150 minutes, but at that point, you can almost see it here. The ranger is beyond the location of the mountain lion. So even though it looks like they do intersect at 150 minutes, the ranger is actually beyond where the mountain lion is. So this is really what we're going to be exploring in the first half of this unit as we look at parametric equations. But hopefully this gives you an idea of what you can do with them. Parametric equations are great for modeling real life motion situations such as this. There's a lot of applications in which you can use parametric equations, and we're going to be looking at how you can go back and forth between parametric equations and putting it into a regular XY rectangular equation. So hopefully you've enjoyed this. Feel free to play with it a little bit more if you'd like, and I'll see you soon.